And you, madam? Hello.
Yes, sir.
Yeah, fine. Okay, now I think this slide is visible. Anjum?
Yes, sir, it's visible, sir.
Yeah, this is, of course, we already. I'm getting echo from. Okay, this is the expression for current in different regions of operation. Cutoff ID is equal to 0 in linear region. Okay, ID is given by so and so, where we have a VDS term also coming into picture because the current depends on VDS also. So in the third case, okay, whenever it is in saturation region, we have ID independent of VDS. And of course, you have seen that okay, this is a PPT which I shared with all of you. So it is AMCD all in one. So mu n is the mobility of electrons. Okay, we are talking about only the N MOSFET. If it is P MOSFET, then this will become mu P. Then this will become mobility of holes. Mobility of holes. Unit is centimeter square by volt second. Cox is unit area capacitance, okay, oxide capacitance, farad per meter square. Mu and Cox is, that's what we call it as Kp, and Vth is threshold voltage, W is the width, and L is the length. This is how do we measure the length and the width of a MOSFET. You can see this happens to be the width, and this is the length of the channel, which is the transistor. Let me just close this. Okay, now fine. Okay. Let me just close this also so that in recording everything is visible. Okay, fine. Is this fine, Anjum?
Sir.
Anjum,
Yes, sir, it is fine, sir.
this is fine. Okay, well, next we just move on to this. Uh, Last class we are talking about representation of MOSFET as a model. So this is again here I'm just specifically calling it as large signal model because I'm not talking about the small signal, that is small v that I applied. So here I have not yet applied the small signal at all. So I'm just simply talking about a model which is for a large signal. When I say large signal, it is the DC current which is relatively high when compared to the small AC signal. So this is the output characteristics of the MOSFET. Now I want to represent the MOSFET in uh, different regions, that is in saturation and linear region. How do I represent the MOSFET whenever it is operating in this linear region and whenever it is operating in saturation region? So in linear region, again, if you can see, Anjum, I have written it as 1 and 2. Can you notice here?
Yes, sir.
So we call it as, even in linear region, we call it as okay, a deep linear region, and this is the normal linear region. So let us just talk about okay, why we named it as 1 and why it is 2 here. So whenever your MOSFET is operating over here, so when does the MOSFET operates here? You can see this is the condition when VGS is greater than VTH and VDS is less than VGS minus VTH. Is it correct? Is this the condition for keeping the MOSFET in linear region?
Yes, sir.
Fine. So MOSFET should be on, but VDS should be less than VGS minus VTH. So we assume that okay, it is somewhere here in this region. So do we say this is the current that is going to flow?
Yes,
This
sir.
is the current that will going to flow. So we know that at the input it is open circuit. Why it is open circuit? Any idea?
V VGS is greater than VTH.
No, VGS greater than VTH doesn't mean that it is open circuit. So VGS greater than VTH means there is a channel created, current starts flowing. Now the point is why we are representing between gate and source an open circuit. So you simply have a voltage. I think last class we discussed about, suppose if you see the structure of your MOSFET, this is your gate. You can see there is an oxide here and there is a semiconductor. Why we are representing this as an open circuit here? Anybody?
No current flows since it's in insulator.
Where no current flows?
From gate, since the oxide is insulator, no current flows from gate to the
That's
source.
what, there is no gate current flowing, so there is no current going into the MOSFET through gate. So that's why we say this is open circuited, because oxide is a insulator, it doesn't allow current to flow. So instead of simply saying okay, current won't flow, I will represent it electrically or electronically as an open circuit. Fine. So this is as well as saying okay, there is an insulator here. So whenever it is open circuit, you can say it is it is not at all allowing current, so which is represented electronically or using circuits using open circuit. Can you see between drain and source I am having a current source,
Yes, sir.
and with the expression exactly same as this. This is exactly same
Yes.
as this. Now I'm specifically calling it as large signal model because I'm considering the DC current. I'm considering the DC current. You can see it is the same expression. There's no change.
Yes.
This is in linear region 1. So next let us see what is the second linear region. I call it as in deep linear region. So why I call it as deep linear region is just notice where I put that region 2. Can you see here? This is region number 2.
Yes, sir.
This is linear. You are going deep into the linear region where VDS is very less. Can you see this is your VDS axis?
Yes, sir.
This is VDS axis. Here itself VDS is less. Now you are going to a region where VDS is very less. So we call it as deep linear region. This is the expression for your what ID in linear region, but in deep linear region is true? VDS is far less than VGS minus VTH because you are operating
Yes.
in okay very less value VDS. So when VDS is very less, shall I neglect this VDS square?
Yes, sir. Because it's very small.
So if it is 0.1 whole square is 0.01. So it is significantly very less. So we will neglect that term. You can see this square term is no more here. ID is now approximately given by this. If we can simplify this, suppose if you make it VDS by ID, this looks like a resistor. Meaning, what I want to say is, can I represent this straight line as a resistor?
Yes, sir.
So in deep linear region, I can represent the MOSFET, the same MOSFET which is over here. I can represent it by a simple resistor between drain and source whose value is given by this. This is exactly simply divide this by what? VDS by ID. So this VDS will cancel out and this will go off and you will end up with this as the expression. Correct?
Yes, sir.
Okay, now we are trying to represent the MOSFET in large signal model once in linear region and second time in deep linear region. So I can represent it by on the distance. Let us see how do I represent this in the saturation region. This is how I am representing this in the saturation region. You know, okay, what is the condition for keeping the MOSFET in saturation? One thing is, what are the two conditions?
VGS should be greater than VTH.
Perfect.
VDS should be greater than VDS minus VTH.
VGS minus VTH should be greater than
Yes.
VDS sat. Fine.
VDS sat.
Okay, now can I represent this particular region again by a current source whose magnitude is given by this equation? Correct?
Yes, sir.
Now, fine. So these are the three representation of MOSFETs in different regions. So I'm representing the MOSFET as a model by this current source if it is in saturation region, by this equivalent circuit representing the drain and source by R on, having this as expression, and this is the representation of MOSFET in linear region, that is not in deep linear region, it is over here, it is given by this expression. Now let us move on to this transconductance. So we are defining this transconductance only in saturation region. This transconductance is useful in saturation region. Why we are interested in saturation region is in almost all analog circuits we try to operate the MOSFET in saturation region. We will come to know, okay, why it is operated in saturation region. Maybe one thing you can write it somewhere in a box. The MOSFETs are used in saturation region for analog applications, whereas the MOSFETs are operated in cutoff and linear region for digital applications. You can make a note of it. MOSFET is operated in saturation region for analog applications because you can have the MOSFET being used for analog applications as well as digital applications. For analog, MOSFET is required to operate in which region? For analog circuits? For analog circuits, where do you operate the MOSFETs?
Saturation region.
For digital circuits?
Cutoff region or linear region.
Cutoff or linear. Perfect. Now, since we are, okay, this particular course, we are using the MOSFET in what? Analog applications. Analog
Saturation.
applications, we consider the ID in saturation region, which is given by this expression. So I will differentiate ID with respect to VGS. I will end up with this. I will end up with this because that's why I will go off. This 2 will cancel with this 2. So you will end up with mu n Cox W by L into VGS minus VTH. Correct?
Yes, sir.
So transconductance is given by. So why it is called as transconductance?
Because we are using a coupling capacitor.
No, there is no coupling capacitor here at all. No, we are simply representing the MOSFET. So there is no, we are not yet gone to what is that amplifier at all at this point of time. Why we are calling it as transconductance? So what is called as conductance? What is the ratio? Okay, what and what is the conductance? What by what is conductance?
ID by VGS.
No, I by V. I by V is conductance.
I by V, sir.
Okay, why it is called as transconductance? That is important. We discussed already. Trans.
Output current and input voltage.
So we are referring to two parameters which are at different ends. So ID is output, VGS is input. So we are referring to two parameters which are at output and input parameters. So that's why we refer it as transconductance. So transconductance for a MOSFET is del ID by del VGS, which is given by, of course, which will be written as GM, which is mu n Cox W by L into VGS minus VTH. Just have a look at these two. GM is proportional to W by L with VGS minus VTH constant, or GM is proportional to VGS minus VTH with W by L constant. What is this W by L constant and VGS minus VTH constant? Why we are not referring to this mu and Cox? Anybody?
So,
Why we are not referring to mu and Cox?
so mu and Cox is constant, sir.
Because no, constant matlab user will not have any decision making power, or he cannot change the values of mu and Cox. Whereas he can change the width of the transistor, he can change the dimension of either width or the length, he can change VGS. User has the option to change only W and L and VGS even practically. So forget about simulation. Even in real fabrication of MOSFET, he cannot change the mu n value, he cannot change the Cox value for a given technology. So that's why this is always kept constant. Of course, in the simulation, we keep it as 200 microampere per volt square. In the same sense, so you cannot, the user cannot have any control on this mu and Cox. So that's why we are not referring here. Whereas you can change the dimension, you can change VGS. Can you change VGS, Anjum? How do you change VGS?
Yes.
How?
Sir, by increasing transconductance.
Hey, come on. VGS. VGS, GM is a dependent parameter on VGS. How do you change VGS? No, you cannot say that, okay, VGS can be changed by changing GM. It's the other way. No, Anjum, you just make this very clear. Since GM is proportional to written as VGS minus VTH, you cannot interchange them and you cannot say VGS minus VTH is proportional to GM. No, that is not correct. No, what I mean here is this is GM is depending on W by L. W by L never depends on GM. Correct.
Okay, sir.
So how do you change VGS in the practical sense? By changing R1 R2s, the biasing resistors, or by changing the battery voltage 0.8, 0.9, 1 volt, 1.2 volts. Correct.
Yes, sir.
Okay, this is how the GM is proportional to W by L, keeping this constant, or you can keep what W by L constant and you can make that proportional to VGS minus VTH. Okay, let us see how do we get these two expressions. Okay, what I'll do, I'll just share the my camera and then try to get okay, let me just share. I think camera is now shared already. Okay, is camera visible? I think it is visible to you.
So it went blank.
Now it will come. Okay, sorry. Oh, now it's fine now. What was the expression for GM? GM was given by mu n
Dou I.
Cox W by L VGS minus VTH. Correct?
Yes, sir.
This is the expression for GM. What I'll do, we know the expression for ID in saturation, which is half into, okay, I will replace, okay, this is mu n Cox W by L VGS minus VTH whole square. Am I correct?
Yes, sir.
Correct. So shall I write it as 2ID is equal to mu n Cox W by L VGS minus VTH whole square? I just simply put this back here. Can I?
Yes, sir.
Shall I do now? VGS minus VTH whole square is equal to 2ID by mu n
Mu.
Cx W by L.
That- Yes, sir.
Can I now write VGS minus VTH is equal to under root of 2ID
2I.
mu n Cox W by L?
Yes, sir.
So you have a VGS minus VTH here. You replace this VGS minus VTH by this term. So what I'll do, I will rewrite it as GM is now equal to mu n Cox W by L root of 2ID by mu n Cox W by L. Am I correct?
Yes, sir.
So can you see here it is what? This is mu n Cox W by L is under root and this is not under root. Can I write
Yes.
this GM as equal to whole under root of 2ID mu n Cox W by L? Can I?
Yes, sir.
Yeah, all of you type in the chat box. Could you able to get this particular not derivation? How do we get the expression for GM? So don't think, okay, I'm going to ask this derivation and this will be for 5 marks. So
So this works only when the MOS is saturation, right?
it is always in saturation. So we are interested in finding the value of GM only when the MOSFET is in saturation. So we never expect the GM calculation when it is other than saturation. You can see this is exactly the one what I've written here. Can you see that this is 2ID? Is it visible? Yeah.
So only the PPT is visible.
That's what. Okay. GM is given by under root of 2ID mu n Cox into W by L. This is what is expected, and that's what I'm getting here. All of you just write it once in your note. Just say, did you people get it or not? So I'm just looking at your answers. So is there anyone who is finding it difficult to get what is this is? So we are trying to rewrite the expression for GM in terms of dimensions of the MOSFET and ID. Because you can see, suppose if you don't know what is VGS minus VTH, one of the equation is this. So of course we are trying to get different equations. One of the equation is mu n Cox W by L into VGS minus VTH. The other possible equation is this other possible equation. One more possible equation is, so okay, first all of you get this equation. Did you all get it?
Yes, sir.
Okay, let me see the next set of equation or one more set of equation for what is that? One more set of equation for GM. Shall I write it as, I'll again start from the same GM. So instead of replacing VGS minus VTH, let me replace this. How do I replace this mu n Cox into W by L using this? So can I write mu n Cox W by L as equal to 2ID by VGS minus VTH whole square? Can I?
Yes, sir.
Okay. If this is so, can I replace this by this? So I'll retain this as it is. I'll retain that as it is. Now what I'll do, I will slightly rearrange the entire thing and then write it as, okay, this is what I have. This is my main expression, the original expression what I had, which is, how did we get this? Del ID by del VGS, correct?
Yes, sir.
So when we replace this VGS minus VTH in terms of ID, we got the expression of GM as this, correct? We got the expression of GM as this. Am I correct?
Yes, sir.
Next, let me replace this part of GM expression by using the ID expression, then try to know it. So shall I now write GM is equal to, what is this mu and C oxygen W bell? Can I write it as 2 ID by VGS minus VTH whole square?
Yes, sir.
Shall I retain this as it is?
Yes, sir.
So does this go with this square?
Yes,
Now
sir.
shall I now write 2 ID by VGS minus VTH? This is one expression. The other expression was under root of 2 ID mu n Cox W by L. The original expression was mu n Cox W by L VGS minus VTH. These are the three possible equations that you can use, okay, depending on what is available while solving the problems. Got the point? These are
Yes,
the
sir.
three different equations what you will be using to estimate the value of GM depending on what is available. Correct?
So how did we get VGS minus VTH in the first equation, sir?
Here.
Yes, sir.
No, upon differentiating. So that's what you got it.
No, sir. Here, GM equal to 2ID by VGS minus VTH square into VGS minus VTH.
See here. Did you had this expression? Let me just take
Yes,
out this.
sir.
Is this is fine?
Yes, sir.
Then I want to replace from this ID is equal to half what mu n C ox W into VGS minus VTH. Can I now write mu n C ox into W by L as 2 ID divided by this? That's what I'm writing here. This
Yes,
is
sir.
2 ID. 2 into ID. That's what is this numerator. In the denominator, you have VGS minus VTH whole square.
Yes, sir.
Got it? Now, you replace this mu n Cox W by L in the GM expression by this. That's what I did.
Okay, sir.
So, you are replacing mu n Cox W by L as 2 ID VGS minus VTH whole square. And you retain this VGS minus VTH as it is. So, this will go, because this is a square, no? I'm taking out the square with this. So, you end up with 2 ID by VGS minus VTH.
Got it, sir.
Okay. I just want to know from all of you, could you all able to get these three expressions of GM? I want each one of you just type it quickly. Yes, 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 no. Keep it here. Take it afterwards. Okay, make it fast. Okay, this is what the expression for your GM is. Okay, let me go to the PPT now. Okay, this is okay. Depending on the availability of parameters, GM can be estimated by any of the three equations because all of them will yield the same, because they have been derived from a single expression. So they will give the same value because that depends on what is the parameter that you have while solving the problem. So this is how you find out GM. So why this GM is required? So let us proceed now. Is this the thing what we discussed last time? MOSFET as an
Yes.
amplifier.
Yes,
Instead
sir.
of VGG, we actually had what? A potential divider to get that required DC voltage. Am I correct?
Yes. Yes,
Now,
sir.
you might have seen that, okay, we thought of, suppose if you apply the, without this VGG, if I apply the input voltage directly, what happens? Hello.
Sir. Yes, sir.
Without this VGG, if I apply the input voltage, does the MOSFET is on?
It is on, sir.
Without this VGG,
No, sir. Without VGG, it will not be
it
on.
will not be on. So in order to keep the MOSFET in on condition, so you are putting some, that's why can you see here, this is shifted up here. From here it has gone down, gone up to this point. Over and above this, you apply this. You can see now I'm writing a point over here which corresponds to GM, which is referring to the value of ID and VGS. So how do you get the value of GM? So you can use any of the three equations and then get the value of GM here. So now this is of course this is how to find the amplification factor. So now we have this as a circuit, this is a circuit, so there is a V in, so I'll take out the V out here. Now I want to see what is the amplification factor of this circuit for this input voltage. What I mean to say is this input voltage is amplified by how much times, how many times it has amplified. So that can be found by writing the AC equivalent. AC equivalent. Now we can see what is the procedure for making the AC equivalent. See here, what is written here?
Short all circuits independent DC voltage.
Short circuit. It is not short all. It is short circuit all independent DC sources. What the purpose of, okay, why we are actually making all independent DC sources as short circuit? Can you remember? Okay, maybe of course I can just take out some other student because you are there with me for a long time. Let me just take, you'll also get tired. What is this, sir is not allowing me to just spot. Okay, Hari Prasad. Hari Prasad. Hari
Yes, sir.
Prasad. Okay.
Yes,
What?
sir.
Why the first condition is required? Short circuit all independent DC sources. Why we have to do this? I think we discussed this last time.
Yes, sir.
Whenever you are doing small signal analysis, that's what. First write the small signal circuit of the amplifier. First condition or first thing to write the small signal model is short circuit all independent DC sources. What do you mean by this?
Sir, to get only AC sources, sir.
Why you want to short the DC?
So for constant amplitude.
No, it is not so, because DC, even though it is higher in amplitude, since there is no variation in that, since there is no variation for AC signal, even though the DC voltage is 1.8 volt or 5 volt or 3 volts, it looks like short circuit. So that's why you can see I had a VGG here, I had a VDD here. Can you just go back here? Can you see there was a VDD, there is a VGG? I'm replacing
Yes, sir.
this by short circuit. I'm replacing this by short circuit. Even though it has got VDD as VGG as amplitude, because they don't have any variation. Am I correct?
Yes, sir.
Since they don't have any variation, I'll replace it by short circuit. So that is first condition. Then what is the second condition? Replace MOSFET by its small signal model in saturation region. You can see now it is, this is a MOSFET, there is an open circuit between gate and source, and you can see
Yes, sir.
now this is GM into VGS. It is not exactly this small signal model, this is not this model. Can you see what is the difference between this and that? Can you see this is the MOSFET model in saturation region for large signal. Can you
Yes,
see
sir.
this is large signal ID, capital ID, but
Yes,
what
sir.
is this? This is a small signal.
Small signal. Yes, sir.
So small signal now is, we know that we have applied some small voltage. Can you see there is small voltage applied? V in.
Yes, sir. Yes, sir. Ween.
If you short circuit this, does the same voltage come across this gate and source?
Yes, sir.
So can you see here? This is the small signal that is applied here.
Yes, sir.
Because of this slope, will you have some ID? Can you see the ID is going here? Now,
Yes, sir.
what is, okay, let me just show you, maybe I'll just show you this, I'll share the camera. 1 second. So you had the MOSFET operating like this. Assume that this is the point where this thing is applied. What is this? Small V in, which is equal to small VGS. So you have a slope here which is giving GM, and suppose this is VGS. So what is the unit of GM? Del ID by del VGS. So is it
Yes,
like
sir.
okay 1 over ohm? This is conductance, no?
Yes, sir. Yes, sir.
So now if you multiply, if GM is multiplied by VGS, what you'll get? This is 1 over
Yes.
ohm. What is this? Volt. What is volt per ohm? Or V by R? What is V by R?
V by
What is V by R?
what is V?
Current.
It is
Sir,
current.
current.
It is current.
Yes, sir.
So that's why we are representing, because of this GM, which is due to the operating region of your MOSFET, and because of the applied small signal, you have some current because you applied a small signal, no? Have
Yes,
you
sir.
not applied a small signal? It
Yes,
ends
sir. We
in
apply.
a small signal ID. Can you see here? I'm writing it as small ID.
Yes, sir.
So if you go to this PPT here, can you see here I'm writing it as GM into VGS?
Yes, sir.
What is this GM into VGS? It's actually a current
Sir.
source.
Yes, sir.
It's actually a current source. That current source is not large signal, but it is a small signal current.
Okay, sir.
Correct? So why this small signal current is flowing? Because of GM and because of applied small signal voltage.
Oh, yes, sir.
Why did you get this GM? This GM you got it because of your applied DC voltage.
Yes, sir.
Correct?
Yes, sir.
All of you keep in mind, you cannot get GM unless you apply DC voltage. And you cannot get small ID unless you apply a small
Small signal.
AC signal, small AC signal. Correct? So to get
Yes,
small AC signal, small AC signal current, you need to have GM as well as small signal voltage. Correct?
yes, sir.
So I'll again go back to this. Can you see now? I have replaced the MOSFET by this small signal model open circuit, and there is a AC current here. This is RD, which is connected to drain, and the VDD. VDD is short circuited, so on. So can you see now? Is this fine now? What I'm trying to do? Just try to see from this to this. Are these two circuits same?
No, sir.
This and this, this and this.
No, sir.
Why? Why they're not same? In what way they are different? Okay, except
Sir,
that
they-
symbol. Except the symbol.
Except the symbol same.
Are they same?
Yes, sir.
You just observe where you're measuring the output voltage. Okay, let me go to amplifier. Are you measuring output voltage here?
Yes, sir.
Is it drain point?
Yes, sir. Yes, sir. Train, sir.
Is this drain here? This one.
No, sir.
Hey, this one. What is
No,
this?
sir.
This is gate, source, drain. This is drain again.
Yes, sir. Yes, sir.
So this is V out, correct?
Yes, sir.
So is this V out still?
Yes, sir.
Is it still V out? Can you see it's
Yes,
the
sir.
same drain point? Now,
Yes, sir.
if you want to know what is V out, when I say V out, it is the voltage at this point with respect to ground.
Yes, sir.
So, if some current I0 flows, I0 into RD, is it not V0? That's what I written here.
Yes, sir. Yes, sir.
V0, the output voltage is now given by I0. That is, I'm assuming a current which is going in, okay, top to bottom through this RD into RD. Is this V0
Yes,
is
sir.
equal to, this is a small signal output voltage, which is nothing but the product of small signal output current multiplied by RD.
Yes, sir.
So can you see there is a current which is going in this direction, and you assumed a current which is going in the opposite direction. Are they exactly opposite to each other? This I0 and this one. Can you
Yes,
see
sir.
this is going down, this is going the other way. So can I write
sir.
this? I0 is equal to minus GM into VGS.
Yes, sir. Opposite, sir. Yes, sir.
This is VGS, correct?
Yes, sir.
Is this VGS same as V in? See here, this is
Yes, sir.
same
Yes, sir.
point,
Yes,
this
sir.
is same point. So can I write I naught is equal to minus gm into v in?
Yes, sir.
Can I replace this I naught expression by minus gm into v in here?
Yes, sir.
Now can I rearrange this? I will take this v in down here. V naught by v in, can I write it as minus gm into rd?
Yes, sir. Yes, sir.
Okay, let me just do it once on a white sheet. You'll get to know. Let me just share it. Maybe on the PPT you're not convinced. Okay, let me do it once so that you can. I just take maybe another 3 to 4 minutes. We started with what? Am I correct?
Yes, sir.
VGG, V in, V naught, is RD. Correct? What is the next step? I will short this. I'll short this. First step. I'll simply short this. This is the first step. I have shorted the independent DC sources. Correct?
Yes, sir.
Next, I'll replace this by its AC equivalent. Am I correct? This
Yes,
is
sir.
V in again. So this is V in. Shall I repeat it as gate? This is plus minus VGS. Can I write this as GM into VGS? This is drain. This is source, which is grounded here. There is a RD. There is a V naught written here. Am I correct?
Yes, sir.
So now, shall I flip it down here?
Yes, sir.
You can see this is gate, source, grounded. There is a current source, GM into VGS. This is VGS plus minus. This is V in, and this is RD. Am I correct? Can you see
Yes,
I'm
sir.
not changing V naught. V naught is a drain point. This is again V naught a drain point. This is again a drain point. This is again drain, source, gate. Is this V naught?
Yes, sir.
So I'm just assuming a current of I naught here. I'm just, okay, let me write some I naught. Correct?
Yes,
So
sir.
shall I now write I naught is equal to minus GM into VGS? Because they are opposite, no? This is GM
Sir,
into VGS.
opposite.
This is minus GM into VGS. So what is V out now? V naught? Is it not I naught into RD?
Yes, sir.
But what is I naught? Is it not minus GM into VGS into RD? Because this RD I'm retaining.
Yes, sir.
So what is this VGS? This is the VGS value. Is it not same as this? Because there is no resistor here. So can I now write it as minus GM into V in into RD? This is V naught.
Yes, sir.
What
Sir.
I'm looking at is V naught by V in, because this gives me the amplification factor. Is it not minus GM into RD?
Yes, sir.
This is what the expression you're looking for. So that's what is done here. So here, this finally happens. So we call it as AV, voltage gain. A stands for amplification, and this is for small v is for small signal gain. So just all of you say, are you convinced with this entire flow, or shall I explain again? Is this fine, or shall I explain again? Just do it quickly. Fine, or once again? Just type in your chat box, is it okay, or shall I do it again? Because this is very crucial. If you can understand this, then you can do whatever you want. This is the only very important concept you have to understand in your amplifiers, how to write a small signal equivalent of a circuit. If you are there, nobody can hold you. We started with the actual circuit, short circuited the DCs, replaced the MOSFET by its AC equivalent, and then made simple corrections, got the expression for V0 by V in, which is exactly the gain, minus GM into RD is the gain. Okay. What is GM expression now? GM can be 2ID mu n Cox W bell. Correct? GM can
sir.
be 2ID by VGS minus VTH. GM can be mu n Cox W by L VGS minus VTH. You can see there are three equations. Depending on the problem parameters available, you can choose any one of them. Correct?
Okay, sir.
So then we'll meet in the next class tomorrow, no? So tomorrow we'll meet and then try to do the simulation of it and then try to verify all this.
Sir,
Yeah,
that current white is negative, sir.
yeah, that's very important because this one you're talking about this white is
Yes,
negative.
sir.
See here,
Yes, sir.
as per your KVL, suppose if you consider, forget about this I1, okay, I0 and so on. So you just take this. You have I1, you have this node, there is a I2. How do you write the KCL expression?
Sir, I1 plus I2 is equal to 0.
Current entering the node is equal to current
Current
leaving the node.
entering is equal to current going out
Okay,
from at a point.
Okay, this is a point. Shall I say what are the currents that are leaving?
I1 and I2.
I1 plus I2 are the currents which are leaving. Is equal
Yes,
to current that is entering the node. Nothing is entering, I will write it as 0.
Yes, sir.
Correct? Now can I write I1 is equal to minus I2?
Yes, sir.
That's what the same thing. See, this is a node. Consider there is some current which is going here, which is GM into VGS. You are assumed a current of I0.
Yes, sir.
So shall I now say I0 is equal to negative of this? As I wrote it here. This is like when now you replace this by I0, replace this by GM into VGS.
Yes,
Correct?
sir.
So shall I now say I0, or maybe this is I2 is equal to minus of I1. Shall I say I0 is equal to minus GM into VGS?
Yes, sir.
Perfect. That's it.
Thank you, sir.
Bye. So thank you all. We will meet tomorrow.
Okay, sir.